Alrighty, hello and good afternoon. Heck yeah, Brianna, you've been waiting for this since office hours yesterday. Homework problem 12 on homework 2 has to do with what we're going to be talking about today. Prathana, I totally can answer that question on this side of lecture as opposed to the other side. So here's the thing to keep in mind when it comes to orbitals housing electrons. So first things first. One orbital, this is the hard and fast rule. One orbital holds 2 electrons. Oh wow, hang on. Gotta get my eraser back. There we go. Holds 2 electrons at its max. So that is absolutely correct. Each orbital can hold 2 electrons max, and it doesn't matter what orbital we're talking about, whether we're talking about s orbitals, p orbitals, d orbitals, or f orbitals, every orbital type holds 2 electrons max. That being said, something to be aware of is there are, for example, 3 p orbitals in the p subshell. Oops. So that means that the p subshell, which is all 3 p orbitals together, hold 6 electrons. All right. Each individual orbital, no matter what the type, holds 2 electrons, but there are different numbers of electrons in each, different numbers of orbitals in each subshell. And so, because of that, the subshells can hold different numbers. The S subshell holds 2, P holds 6, D holds 10, and F holds 14, because of the number of the number of orbitals present in each subshell. All right, but each orbital holds 2 electrons max. Hopefully that clears things up and makes a little more sense. All right, now we have a cliffhanger to pick up on, and we are rapidly approaching the end of chapter 3. All right, this is going to be our last lecture in chapter 3, and then we will dive on into chapter 4. We left things with, we had written out the electron configuration of argon, which argon has all the electrons of neon, plus a full 3s subshell and a full 3p subshell. And then we wrote out magnesium. And magnesium has all the electrons of argon plus 4s2. All right? And we said this was confusing because we asked where are the d orbitals? Where's the d subshell? We know that the d subshell becomes available in the 3rd shell, right on the 3rd energy level. But yet, with the electron configuration for magnesium, we fill the 4s subshell before while we still have an empty d subshell, and we asked why that is. Well, the answer to that question is the 4s subshell is slightly lower in energy than the 3D subshell. All right, the 4s subshell is slightly lower in energy than the 3D subshell. All right, they're very close, but the 4s is just slightly lower, so it fills first. So the order in which orbitals fill are: you fill the 3s, 3p, 4s, then you jump to the 3d, and then you fill the 4p afterwards. Now, if you're wondering, you're going, gosh, this sounds confusing. This sounds like it's going to be a pain. The cool thing is, you wrote yesterday in lecture, you wrote the correct electron configuration for magnesium without knowing this. All right? The periodic table will automatically, if you use the periodic table to write out your electron configurations, the periodic table will lead you to the correct electron configuration naturally. All right? The one thing, the one detail that you have to keep in mind is right here. It's when you go from the S block to the D block. All right? When you cross over from the S block into the D block, the D block, this is the one thing you have to remember, is always one shell lower than the S subshell. All right? The D subshell is always one shell lower than the S subshell. Let's do a few examples so you can see what I'm talking about. All right? Let's write the electron configurations. Oops. Let's write the electron configurations for the following elements. Okay, Angela, let's see. So we use argon in a block when finding magnesium instead of yes, exactly. Exactly. That is correct. Air saves us a ton of writing. Okay, Susan, why doesn't magnesium refer back to neon since neon is... Oh, sorry. Susan, great catch, and my bad. Yeah. This is okay. I apologize to all of you who are looking on in shock and horror and wondering why why I was talking about magnesium instead of calcium. Sorry, let me just use a clarification. So I flubbed up. Magnesium is neon 2s2. Oh, sorry, 3s2 right? Because magnesium is 1, 2, 3 down on the third period. And all of you who saw this, you were totally right. Calcium was the metal that I meant to compare it to. Calcium is argon 4s2. My bad. One further space down. That is the one I meant to do. Yes, you did learn something. You both did. And you know you've learned well when you can spot your instructor making a mistake. If you can catch me, then you know that you know. And that is my poor embarrassed face palming self. Carenza and Susan. Well done. Okay. Calcium, not magnesium. All right. Let's do a few examples. Writing the electron configurations for some D block elements. So let's start with let's write the electron configuration for vanadium. All right, we're going to take this step by step like we did yesterday. Step 1 is we need to locate where vanadium is on. Oh, sorry. Okay, so vanadium is number 23 if you haven't located it yet on your local periodic table. Its nearest noble gas with fewer electrons is argon. So we are going to use argon for our noble gas abbreviation. All right, so that is step 1 and step 2. We've found its nearest noble gas with fewer electrons. Now vanadium is 1, 2, 3, 4, down on the 4th period. All right, so we need to count our way over. We're going to go 1, 2. All right, so vanadium will have a full S subshell. We go 4s2. All right, now this is where you need to keep your wits about you. Every time you cross from the S block to the D block, you want to hear this little alarm bell going off in your hair or your head, because there's something that you need to remember. Over here in the S block, we may be dealing with the 4s, but when we cross over into the D block, the D subshell that we're filling will always be 1 energy level lower than the S. So we cross from calcium to scandium. That's 1, 2, 3. We are 3 spaces into the D block. So this will be 3D3. All right. And your shell of the D block that you're filling will always be 1 shell lower than the S subshell that you just filled. Right, so the electron configuration for vanadium will be argon 4s2 3d10. All right, let's do another example. Let's go with palladium. Oh, well, but not in yellow. There we go. Let's do palladium. So first we have to find palladium on the periodic table, and it's right here, number 46. Its nearest noble gas with fewer electrons is krypton. So we're going to start by writing krypton as the noble gas abbreviation. Yeah, Jen, when crossing that invisible drops your orbital energy by 1. All right, and that invisible D line is what separates the S block from the D block. All right, so let's find the period palladium's on. It is down here 1, 2, 3, 4, 5 on the 5th period. All right, so we need to start by counting our way over. We're going to go 1, 2. So this will be 5s2. And then we're crossing over. Whoa. Crossing over this line, so we move from the 5s to the 4d, because the D subshell we're filling is always 1 energy level below the S subshell. And this is 1, 2, 3, 4, 5, 6, 7, and 8. 8 spaces in, so this will be 5s2, 4d8. All right, that'll be the electron configuration for palladium. All right, let's do another example. Let's do a fan favorite element. Let's do arsenic. All right, arsenic AS is right here, number 33. Its nearest noble gas with fewer electrons is argon. All right, let's locate our period. 1, 2, 3, and 4. And again, we got to be careful because here we're crossing from the S block into the D block. So we go 1, 2. We've got a full 4s subshell. So that'll be 4s2. And now we're crossing over 3d. And to get to arsenic, we have to move 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We cross through the entire D block, so this will be 3d8. But now get this. We've got to cross from the D block into the P block again. And when we do, we have to go 1, 2, 3 spaces in. Something to keep in mind, the P block that you're filling will always be at the same level as the S block that you're filling. So this will be 4p3. All right, now the reason why these are the same is, remember, we're using argon as our noble gas abbreviation. Argon already has filled the P subshell, right? So we can't, after filling the 3D subshell, go to 3P because that's already full. We've got to bump back up into the 4th shell. So we put our remaining 3 electrons in the 4P subshell. Cool? My apologies, I thought my phone was on silent. Okay, so that is that is a intro to writing electron configurations with D block elements and elements on the 3rd period and lower. Let's go ahead and write in our orbital diagrams for these. All right. So for vanadium, here we're dealing with the 4s subshell, And the 3D subshell. Now there are 5 orbitals in the 3D subshell. 1 orbital in the 4s. So we've got 2 electrons in the 4s. Then we have 1, 2, 3 electrons in the 3D. So that would be the orbital diagram for vanadium. For palladium, for palladium, we've got 2 electrons in the 5s orbital, and we have 8 in the 4D subshell. So we go 1, 2, 3, 4, 5, right? Singly filling all of our orbitals, trying to make as many electrons have their own room as possible, but we still have 3 electrons left, so we have to go back and add 3 more, so that would be the electron configuration for palladium. And then for arsenic, we have the 4s subshell. We have our 5 orbitals in the 3D subshell, and the 3 orbitals in the 4p subshell. So we've got 2 electrons in the 4s. We have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 in the 3D subshell. And then we have 3 electrons. 1, 2, 3 in our 4p subshell. All right. So those are the orbital diagrams that pair with the electron configurations that we just wrote out. All right, let's do just a couple more examples and then we'll dive into chapter 4. But let's just get a few more reps in writing these electron configurations. All right, let's do let's do bromine is a good one. Let's do bromine. So first we got to find it. Right, bromine is right here. Its nearest noble gas with fewer electrons is argon once again. Let's locate the period bromine lies on. It is on the 1, 2, 3, 4th period, right? So we're going to start with our 4s subshell, and we count 1, 2 spaces in. So that'll be 4s2. To get to bromine, though, we've got to cross over into the D block. So this will be 3D, because we got to drop our energy level by 1. 3D 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. A full D subshell. Now we have to cross back from the D block into the main group. We just finished our 3D subshell, so now we're going to be filling our 4P subshell. And we move 1, 2, 3, 4, 5 spaces in. So this will be 4P5. All right, that is the electron configuration for bromine. Let's do another one. Let's do ruthenium's a good example. First, we have to locate ruthenium, Ru, which is right here, number 44. Its nearest noble gas is Superman's home planet of Krypton. We throw that in a bracket. Ruthenium is on the 5th period. All right, so we're going to start by filling our 5s subshell. And that will be a full 5s subshell. It's time to cross from the S block into the D block. So that will mean we're dealing with our 4D subshell. And to get to ruthenium, we move 1, 2, 3, 4, 5, and 6 spaces in. So that'll be 5s2, 4d6. All right. Now let's take, with these last two examples, let's write out our electron configurations. So for bromine, we have the 4s subshell, the 3d subshell, and the 4p. And here we have 2 electrons in the 4s. We have 10 electrons in our 3d subshell. Then we have 5. 1, 2, 3, 4, and 5 electrons in our 4p. So that is the orbital diagram for bromine. Now let's do ruthenium. Okay, sweet. Okay. So we have our 5s subshell with 1 orbital, our 4d subshell, which has 5, and here we have 2 electrons in our 5s, and then 1, 2, 3, 4, 5, and 6 electrons in our 4d. So again, electron configuration, orbital diagram. All right. Now, at this moment in time, you can tackle any electron configuration that that I can throw at you. With this base of knowledge, you know how to handle the D block. You know how to handle the main group. In this class, the book didn't go into writing electron configurations for F. Did do S block elements. It did not cover F block elements in the textbook, so we will be omitting that. If you take Chem 400 with me or someone else, you'll probably get into it. So there is more to talk about, but this is all this textbook covers, and so this is all I'll be covering. Okay, Angela has a question. With orbital spins, would you say that bromine and ruthenium has an electron up spin? Okay. So Angela, great question. So actually, the spin's direction is relative. In other words, you could draw. So the spin's direction is relative. You could draw these with spins down, and the answer would be just as correct. So we wouldn't really call these spin up or spin down, so to say. But what is important, and I think this might be what you're getting at, is what we can say about both bromine and ruthenium is they have unpaired electrons. And that makes them radical species. So we don't really say spin up or spin down because you could draw them with the spin down and it would be just as valid. But what is important is that they have unpaired electrons, and so that makes them radical elements. So that would be the important thing to focus on, that there's unpaired electrons more than the direction, if that makes sense. All right. Totally. You are welcome. Oops. Here we go. Anytime. Okay, so with that actually brings chapter 3 to a close. All right, and so with chapter 3 under our belt, we are ready to dive in to chapter 4. And chapter 4 is about one thing and one thing only. And that topic is the topic of ions. All right. Okay. So we are going to be discussing ions, all their aspects, all aspects of ions in chapter 4. One thing that I want to point out, for those of you who read the book, I know the books, I find it a helpful study tool. Not every student does, but I know many of you do. So the order in which I'll present the material is going to be out of order from the book. So, there we go. So I'll be presenting this material in an order different than the book. So for those of you who read along, who use the book to study, rather than, you could totally read the book from where it starts to the end of the chapter, and you'll actually read sections before I cover them in lecture, and that might be good. That might be a totally solid way to study. But if you like to read the material that we've gone over in lecture, then I recommend just looking at the chapter headings and go like, oh yeah, we talked about that. No, we haven't talked about that. Because I kind of present this material in a slightly different order than the way the book does, and I wanted to give you a heads up. All right. So with that being said, if we're going to talk about ions, it'd probably be a good idea to know what ions are. All right, and an ion is an atom. And just for completeness sake, or group of atoms, to eventually. So it's an atom or group of atoms. Oops. That has a net charge. All right, let's talk for a minute about what I mean by net charge. All right, so a net charge arises from an imbalance in protons and neutrons. A species will have a net charge if the number of protons are greater than the number of electrons, or if the number of protons are less than the number of electrons. All right? If the number of electrons are greater, then you'll have more negative charges than positives, right? So this would be give you a negative ion. And if you have more protons than electrons, that means you have more positive charges than negative charges. You will have a positive ion. All right. So so let me show you what I mean. All right. So for example, consider the atom. Oops. No. Consider the atom sodium. All right, let's consider a sodium atom. So we go. So if I asked you how many protons sodium has, you'd look at the periodic table. You'd say, oh, sodium has 11 protons. And if I asked you how many electrons does it have, you can say, well, neutral elements have the same number of protons and electrons. So it has 11 electrons as well. Now, when you look at, you calculate your net charge by adding all the protons and electrons in your species together. And we have a positive 11 from our 11 protons, and we have a negative 11 from our 11 electrons. So our net charge here is 0. Sodium, the element, is net neutral. Now, let's compare this. No, that looks like an S. I meant it to be a versus. So let's compare this to, let's say we have an atom of sodium that's lost an electron. Let's say somehow through some chemical process it has misplaced its electron, maybe left it with its keys in the car. So let's say we've lost an electron. So sodium will always have 11 protons, but if it's lost an electron, that means there's only 10. And if you calculate your net charge for a sodium atom that's lost an electron, we have a positive 11 from our protons, but we only have 10 electrons, so that's a minus 10. And here we do have a net charge. We have a net charge of positive 1. So we write that net charge next to the elemental symbol. All right, this right here is the net charge. Now, there's actually 11 positive charges in this sodium ion, but because there are 10 electrons, 10 of the negatives cancel 10 of the positives, only one positive shines through. So that is where you write the next net charge of your ion. All right. Let's in a very similar example, let's take a look at an atom of fluorine. All right. So fluorine has 9 protons and 9 electrons. And if we calculate our net charge, if we calculate the net charge, we have positive 9 for all of our protons. We have a negative 9 for all of our electrons. This has a net charge of 0. All right. Now, let's put this in juxtaposition to an atom of fluorine that has gained an electron. All right. Fluorine will always have 9 protons because that's what makes it a fluorine. If it's gained an electron from somewhere, maybe it found it walking through the park, sitting at a bus stop. If it's gained an electron, then it'll have 10, right, instead of 9. And our net charge here will be, we have 9 protons, so that's a total positive charge of 9. And we have 10 electrons. Oops. So positive 9 minus 10 gives us a net charge of negative 1, and we write that superscripted to the right of our elemental symbol, just like so. Just like we did with sodium. That is where, whoops. That is where we write the net charge for this ion. Okay, let's see, Prarthana. Will the number of protons and electrons be given? I'm going to give the most unsatisfying answer that any student could ask for. I'm going to say you'll see. So hold that thought. Let's wait until we get into actually doing examples. All right, here I'm just introducing the concept of what a net charge is, what it arises from. But you'll see in examples that all the information you need is actually on the periodic table, and you'll always have a periodic table. So we'll get there, but let's hold that thought for a minute. Okay, let's see. So we've got so those are what ions are, right? Ions arise when you have an ion when you have a net charge, right? Net charges arise from an uneven number of protons and electrons. And before we leave this topic, I want to say that ions actually come in two flavors, all right? Just like we saw with sodium and fluorine, right? Sodium had a net charge of 1. Actually, I should be calling this fluoride because it's anionic. So ions come in two different flavors. You have the positive kind, like sodium, which we call cations, and then you have the negative variant, like fluorine, which we call anions. All right, so ion is a general word that can relate to any species with an imbalance of protons and electrons. But if you want to be specific, a cation is an ion where there are more protons, so it's positive, and an anion is an ion where there are more electrons, so it's negative. All right, so that's kind of an introduction to what ions are. Let's talk about how they form, where they come from, and why would an atom, this is a question, why would an atom want to have an unbalanced charge in the first place? Why wouldn't it want to have the same number of protons and electrons? And the answer to that question actually lies right here in the periodic table, and not just the table in general, but specifically here in the last column of the periodic table. So this column of the periodic table has a name. These are called the noble gases. All right, these are the noble gases, and they are insanely stable. All right, they are crazy stable. All right, they're crazy stable, and they are the reason why the main group elements form ions. Okay, the noble gases are crazy stable. Another Another word for stable is unreactive. All right. We say that they're unreactive or inert. All right, and these two meanings are linked. Another way to saying stable is they're unreactive. They're unreactive because they just don't react. They can't engage with different compounds, different elements around them. There could be reactions going on, explosions going on, and the noble gases will just sit there kind of like zenned out, just like they don't react to anything. You can't get a reaction out of them. And the reason why they're so stable, their stability comes from their electron configuration. One thing you'll notice about every noble gas is that each noble gas has a full subshell. Has a completely full what we call valence shell. All right. When you look at helium, for example, the electron configuration for helium is 1s2. If you look at neon, 2s2, 2p6. If you look, let's see, I need to scoot these down just a little bit. All right, if you look at argon, for example, we've got a neon core, and then it's 3s2, 3p6. If you look at krypton, we've got an argon core, and here we're 4s2, 3d10, 4p6. All right, every single one of these electron configurations have completely full shells, right? Each shell with electrons in it is filled to the max, all right? And there's something incredibly stable about that, so much so that every other main group element wants to have the same electron configuration as its nearest noble gas, all right? And that is something we call the octet rule. And the reason why we call this the octet rule is if you look at the number of electrons in each valence, all right, when you look at the highest energy shell for every noble gas, you have 8 electrons present. Right? For every single noble gas, you have 8. Oh, wait, no, hang on. There's only 2 electrons for helium. But that's the one example. Every other noble gas on the periodic table has 8 electrons in its highest energy shell. All right, and that quality, yes, totally. Say that is exactly it. If you're wondering why we use the noble gases for abbreviations for electron configurations, it's because the noble gases are like the definition of stability on the periodic table. And so that is kind of the base, the standard that all these other elements want to live up to. All right? So the fact that all other main group elements want to have the same configuration as a noble gas, we call the octet rule. And we do it because, with the exception of helium, every other noble gas has 8 valence electrons. So helium has 2, everyone else has 8. All right, so the excuse me. The octet rule is this. Every main group element wants to have, sorry, that just looks like an M. Let me fix that. The same number or I should say the same electron configuration as its nearest noble gas. Right. Every main group element wants to have the same electron configuration as its nearest noble gas. This is the octet rule. And the drive of every atom to attain that electron configuration is what causes them to gain or lose electrons. All right. And the cool thing is this. All right. And Parthana, this is kind of getting back to the question that you asked. Will I tell you the number of protons and electrons? The cool thing is you can determine an element's cationic or anionic charge by looking at its position on the periodic table. All right, you can determine an element's anionic or cationic charge by looking at its position on the periodic table. Let's do a few examples so you can see what I mean. Carenza, that is a great question. For electron configurations, right, it is always the nearest one with fewer. For ions, it could come before or after. It depends. All right, and you'll see this here. I don't know why, but I have always lectured with the periodic table on this side of my slide, and so for whatever reason, having it on the other side makes me feel all out of sorts. And now I've just given you a brief glimpse into my neurotic side. Yes, Jen, the plot thickens. Exactly. Okay, so for the following example, I'm going to task us with determining. We're going to need to determine the ionic charge of totally and of and this is where the fun begins. So first let's look at oxygen. There we go. let's see. Yeah, that's, you know, Carenza, that's exactly, that makes perfect sense. Probably we read right to left, and so having it over there is just the natural part of having grown up reading English. Anyways, let's determine the ionic charge of, and our first element is oxygen. So check this out. Now, if you're worried, like, oh my gosh, do I have to write out a bunch of electron configurations? You don't. All you have to do is locate oxygen, who has 8 electrons, right? And you can see that from the periodic table. When it's neutral, it is 8 electrons. Oxygen's nearest noble gas is neon, all right? So oxygen wants to be like neon with 10 electrons, right? So ask yourself, does oxygen need to gain electrons or lose electrons? And the answer here is oxygen needs to gain, right? It needs to gain 2 electrons. And when it does, it will pick up a charge of -2. So the anionic charge that oxygen will acquire is -2 because it wants to bounce 2 spaces up to its nearest noble gas. It gains 2 electrons, picks up 2 negative charges, so it has a charge of -2. All right? Let's do the same problem, different element. Let's look at, whoops, nope. New slide. Let's look at bromine. All right. Now bromine, let's find this guy. Number 35, right? Bromine has 35 electrons. It wants to be Superman's home planet of Krypton, right? 36. So bromine needs to gain 1 electron, right? It needs to gain 1 electron. That means that as an ion, bromine is going to pick up a charge of -1. So the ionic charge bromine will develop is -1. All right, let's do another example. Let's look at sodium. All right, sodium is right here on the periodic table. Now, sodium has 11 electrons, and the closest noble gas to sodium is actually behind it. It's neon. Sodium has 11 electrons, but it wants to be like its nearest noble gas, which has 10. So here, sodium, to have the same electron count as neon, to have that electron configuration, sodium needs to lose 1 electron. Now, what happens when you lose 1 negative charge? Well, you're going to have an excess of positive left over. If you lose 1 negative, that means the charge of your species will be +1. So sodium is +1. Okay, Angela. So ions and their charge are kind of based on how the element can... Yes! Exactly. Angela, I could not have said it better myself. Main group elements become ions to acquire the stable electron configuration of their nearest noble gas. Okay, Jen. Is this called a valence charge? The table I'm looking at is giving me the same answers. I've never heard the term valence charge used, but it sounds like it sounds like the same thing. And it would make sense because we're talking about the valence electrons, the electrons that are furthest from the nucleus in the highest energy shell. Totally. These are excellent questions, excellent comments. Let's do another example. Let's determine the charge that calcium will develop. All right? So let's identify calcium. All right, it's right here, number 20. On the periodic table, calcium has 20 electrons, and it wants to pick up, so we've got to find its nearest noble gas, which is going to be argon. All right? So it wants to be argon with 18 electrons. And since calcium is sitting on 20, that means if it's going to gain that, heck yeah. Oops. I keep hitting the @ button instead of the exclamation button. I don't know why when I'm typing things out. Probably because I'm typing while trying to hold this, which is harder than it sounds. So calcium, 20 electrons. It wants argon stable 18 electron configuration. So it needs to lose 2 electrons. All right? It needs to lose 2 electrons in the process. So when it does, right, if you lose 2 negative charges, you're going to be left with 2 positive charges. And so calcium will develop an ionic charge of positive 2. All right. Now, if you're looking at this and going, okay, Josh, we're getting it. When are you going to hit us with the next level? When are you going to give us a problem that's like hard? Well, I'm so glad you asked, because I am about to give you the hardest element on the periodic table to determine. This is as bad as it gets. Let's figure out the charge that aluminum will have. All right. Now, here's why aluminum is the hardest. Aluminum has 13 electrons. All right? And when you look at aluminum, you may be tempted to say, oh, my nearest noble gas. My nearest noble gas is argon, with its 18 electrons. And here's the thing, don't fall for this trap. Argon looks closest on the periodic table, but it's not. Neon is actually closer to argon. Because look at it, neon has 10 electrons, it's 3 electrons away from aluminum. Argon has 18, it's 5 electrons away. So don't make the mistake of going like, oh, they look close. Actually look at the number of electrons. Neon is closer. All right. So because neon has is the closest noble gas to aluminum, that means that aluminum, to to become stable like neon is, aluminum needs to lose 3 electrons. So it will pick up a charge. If it's lost 3 negatives, it will have a remaining charge of positive 3. All right, and that is the worst one I can dish out as far as these examples go. Cool? All right, let's see where we are. Okay, I think I'm looking at the next topic. We're about to get into naming ionic compounds, but I'm looking at our time, and I think I'm going to save these for tomorrow. Okay, Angela. Angela, excellent. Observation. With an exclamation point, not an at symbol. Okay, let's look into that. So Angela's question is this. What about silicon? Which is right here. What is silicon's closest noble gas? Is it argon? Or is it neon? Well, if you look at silicon, silicon has 14 electrons. If you move 4 spaces to the right, you find argon with 18. But if you move 4 spaces to the left of silicon, you get neon with 10. All right, both of these are 4 electrons away. All right, and the same is true, by the way, for carbon, for example. Exact same story. It turns out that silicon and carbon can be anionic or cationic, so they actually have a choice. They could be anionic, they could be cationic, but usually they choose to be neither. All right, silicon and carbon at times can be cationic, at times they can be anionic, but usually they choose to be neither. Silicon and carbon tend to prefer, they don't like to ionize, they'd rather not be an ion. And if you're wondering, well, then what are they if they're neither? You will have to stay tuned for us to get to chapter 6. Chapter 6 we'll talk about all about what elements do when they're not being ions. But chapter 4 is about ions. Sorry, chapter 5 is where we'll talk about the elements that choose neither to be cations or anions. So, and then I guess coming around and answering your question fully, Angela, I'll never... Yeah, yes, exactly. Exactly, Susan. They are hipster nonconformist atoms. They could be this, they could be that. They choose to be neither one. They pick door number 3. We'll be talking about them in chapter 5. And then, Angela, circling back to answer your question in full, I won't test you in the context of ionic compounds. I'm not going to give you carbon or silicon because it's ambiguous. They could be, they could go either way. So you won't be tested on those two. Totally. Okay, that's where we'll pause the new material. We'll come back tomorrow and talk about naming compounds, and we should be able to to finish off Chapter 4. Chapter 4 tomorrow. Dang, the semester's going very quickly. A couple pieces of business, actually, I totally blew right past them at the beginning of lecture. Something weird happened with the extra credit assignment. I said in the post that it would be due on the 22nd, and something happened where it in Canvas it was displaying that it was due on the 15th. I corrected that. That link is open. Also, if anybody tried to click the link to the lab video number 4, that link went dead. I revitalized it, so it's working again. I think those are the two main pieces of business. I'm just opening up my notes to see. Also, Lab 5 went live today, which deals with stuff. Lab 5 deals with Chapter 5 material. So we're still a ways away, but it's there for anybody who wants to be an early bird and catch the worm. Anyways, if there are no questions last minute, I'm going to go ahead and put a pin in lecture here. Thank you, everyone, for dropping by, for asking great questions. Thank you, everybody who's watching a little bit later after the fact. I hope you have a great, what day is it today? Wednesday. And I'll catch you all tomorrow, same time. Alrighty. Later.